Hello. Today we'll be looking at AC circuits and focusing primarily on RC series circuits. That's resistors and capacitors in series. Now, when a capacitor is connected in an AC circuit, its opposition to the flow of current is determined by its capacitive reactance, denoted by XC. There's an inverse relationship between the frequency of the supply and its reactance, its capacitive reactance. And this relationship is given as XC is equal to 1 over 2 pi FC, where F is the frequency of the supply and C is the capacitance of the capacitor. Of course, the frequency measured in hertz and the capacitance in farads. Now, when we connect a capacitor and a resistor together, as shown in our circuit, we're dealing with series circuits. So we connect the resistor and our capacitor together. At the time we close the switch, for this circuit, the current through the circuit, which is, since it's a series circuit, which is also the current through the capacitor, will be a maximum. And this current will be given by Vs, which is our supply voltage, divided by R. Now, if at that point in time, all the voltage will be seen across the resistor, then it means that the voltage across the capacitor at that time is 0. Now, if we're seeing a maximum current, the current is a maximum through the circuit, the voltage across the capacitor is a minimum. In effect, what we are saying is that the voltage across the capacitor is lagging the current through the capacitor. Or we are seeing voltage, or we're seeing current before we see voltage. All right, lagging. The voltage across the capacitor, we will see that after we have seen a current through the capacitor. And that's why we say. The other way of putting it is that the current is leading the voltage across the capacitor. At the same time, the voltage across the resistor, which follows the current, will be at its maximum, meaning at the point I close the circuit. Okay, so bearing this in mind, we can consider this phasor diagram, which represents the relationship between the voltage across the capacitor, the voltage across the resistor, and the circuit current. We're also showing the phase angle phi and the supply voltage V. Now let's discuss these relationships. Firstly, the circuit current, which is I, is in phase with the voltage VR across the resistor. As I mentioned before, at the time I close, the circuit current and the voltage across the resistor were in alignment. And we're defining that as being in phase. So there's no angular displacement between the two. The circuit current, however, is leading the voltage VC, which is across the capacitor, by 90 degrees. So the circuit current is leading the voltage across the capacitor by 90 degrees. I can therefore determine the supply voltage because at all times, the supply voltage, Vs, is equal to VR plus Vc. So at all times, the supply voltage is equal to the sum, vector sum, of course, of the voltage across the capacitor and the voltage across the resistor. And what we have here formed, yes, with Vs, Vr, and Vc we now have a right angle triangle. So we can find that resultant Vs by applying Pythagoras' theorem. So by Pythagoras' theorem, Vs squared plus Vr squared is equal to Vc squared, or Vs is equal to the square root of Vr squared plus Vc squared. And we know that from Ohm's law, the current is the ratio of the voltage to the resistance, which is also true for the capacitor, meaning that the voltage is equal to, or the current is equal to the ratio of the voltage to the reactance. So we can make those substitutions for both VR and VC. Substituting these relationships into our equation, we see that ISZ, and I'm now introducing a new term, ISZ is equal to IR, R times R, all squared, which as we indicated before, that would have been VR, and IC times XC, which would have represented VC, all squared. Because we're dealing with a series circuit, all these currents are equal. So IS is the same as IR, which is the same as IC. So I can remove those, and I am left with this expression that Z is equal to the square root of R squared plus XC squared. And Z, special name given to Z, is the impedance of the circuit. Now, the impedance of the circuit would be the overall opposition to the flow of current provided by the circuit. But the item or the component within the circuit that is making the great difference here would be your XC, or meaning your capacitor. But because we were looking at this vector sum, and we have talked about leading and we have talked about being in phase, it is important that we determine the phase angle, or the angle between the supply current and the supply voltage. Very important bit of information. And so the phase angle phi is the inverse tan of XC over R, given that we have a right angled triangle. And so phi is equal to the inverse tan of XC over R. So importantly, we have been able to determine Vs. So Vs, supply voltage, is equal to VR squared plus VC squared. We have also been able to determine Z. Z is equal to R squared plus XC squared. And of course, we have here phi, phase angle, or the angle between the supply current and the supply voltage. So let us look at this example and see if we can apply everything that we just looked at. The circuit shows a 530.5 microfarad capacitor connected in series with an 8 ohms resistor across a 30 volt, 50 hertz supply. Determine the current flowing through the circuit. Now, this is micro in the circuit, but we are showing nano here, so we make that correction, okay? So it's 530 microfarads. So in order to determine the current, we know that current is going to be equal to V supply over Z. So we need to find Z. So Z, the impedance, is equal to the square root of R squared plus XC squared. We already have the value of R, so we need to find XC. And XC is equal to 1 over 2 pi FC. That's 1 divided by 2 pi times 50 times 530.5 times 10 to the minus 6. And that is equal to, we punch that in. Okay, and that is equal to 6 ohms. Okay, so Z is equal to the square root of 8 squared plus 6 squared, which is equal to the square root of 64 plus 36, and that's the square root of 100, equal to 10 ohms. So the magnitude of the current, I, is therefore equal to V over Z, which in this case is 30 over 10, which gives us 3 amperes. However, we also need to find what's the phase angle between the current and the voltage. So phi is equal to the inverse tan of 6 over 8. That's the inverse tan of 0.75. We put that in. And that gives us 36.86 degrees. Okay. So the final answer, as we were asked to find the current, the final answer is that I is equal to 3 amperes at 36.86 degrees. However, we rarely write our answers looking like this. So I is equal to 3 at 36.86 degrees amperes. And this should also be noted that this 36 degrees is leading. So another way of writing it is that I, now the positive is indicating that it is leading. So I is equal to 3 amperes at 36.86 degrees leading. And if we were to show that in terms of a diagram, then if I is on that axis, then it means that this is V, this is I. So the angle between V and I, this would be 36.86 degrees. I thank you very much for your attention.